Module 2, number 3, Nodal and Mesh Analysis. So first of all, please be fully aware that we finally start to analyze the circuit, which is the core of this course. So we are going to introduce two alternative techniques to achieve the current or voltage at anywhere in the circuit: nodal and mesh. Mesh analysis is also called loop analysis. So first of all, let's learn nodal analysis, see how it works. Nodal analysis is actually stated as, first you want to apply in the KCLs. Be careful, it's KCL at nodes in the circuit to come up, obviously, bunch of equations. And the second, you need to basically rewrite those currents in the KCLs in terms of node voltages by applying Ohm's law. So we will see how we implement these two steps one by one. Both nodal and mesh analysis are for finding voltages at all nodes and currents along all branches. The best way to learn this is obviously having an example going through. So this is the circuit example. Let's see how we conduct the nodal analysis. First, we need to write the KCLs at nodes. Let's take a look at this circuit. How many nodes we have? In other words, where we can really write KCL at. If you recall the definition of nodes and then come back to this circuit, you should come up with these nodes. 1 through 5, up to 5 nodes in the circuit. Okay. Different nodes have different voltage potential. Okay. This is the key to differentiate node. And for that reason, the bottom multiple points are actually the same node, since, again, they share the exactly same voltage potential. So we call it as a super node involving more than one point, but actually they are having the exactly same voltage potential. So single node. So 1 through 5. Now let's write KCLs one by one for them. You feel free to pause the video and try to write KCLs. And we have two alternative ways to write KCLs. But here I'm just applying the second statement. For example, at node 1 here, we obviously have the current entering the nodes I 12 volt equals to the total of current leaving it, which is I1. So here we go for first KCL at node 1. Similarly, at node 2, we have current entering the node I1 equals to total of current leaving it, which are I2 and I3. Here we go. At node 3, we have entering the node current I3 itself equals to leaving current I4 plus I5. At node 4, we have entering the node I5 equals to leaving current I3KO. At the bottom node, number 5, we have the current entering the node is I2, I4, I3K. The current leaving node 5 is I 12 volt itself. So here we go. Up to 5 nodes and up to 5 KCLs correspondingly. From these KCLs, we can move forward. But before that, there's one thing I want to clarify and emphasize. In the rest of the class, we will assume the bottom node, which is 5 in this particular circuit, as ground, unless otherwise labeled or stated. Okay? Because in a lot of circuits, if you check the textbook as well, there's no ground labeled, and therefore we have to assume one as the ground. And the bottom node, like this here, node number 5, is the ground. Okay, so keep this in your mind. All right, let's take a look at these 5 equations. The first equation here is basically telling you the current through 12 volts is equal to the current through 9 kilo ohm. It is something very easy to know if we observe the circuit, that the 9 kilo ohm is series connected with 12 volts voltage source. So their current, of course, identical. So to reduce the number of unknown in the equations, we can only keep one of them. For example, we just keep I1. And also knowing the current through 12 volts voltage source is nothing but I1. Same thing happened at equation 4 here. We keep Y5 and keep in mind that 3 kilo ohm current is nothing but I5 as well, due to the series connection between 9 kilo ohm and 3 kilo ohm. Another thing is, let's take a look at the very last ground node KCL. What trick this equation has? Well, if you add equation 1, 2, 3, 4, all of them up together, you're gonna end up with this 5th equation. In other words, if you add up I12 volts, I1, I3, I5, them together, and then place this sum at one side of the equal, and then add I1, I2, I3, I4, I5, I3K, them together, and then place the sum at the other hand of the equal. The result gonna be this equation. So basically the 5th equation, this guy is derived by previous 4 equations. If you recall some basic knowledge from algebra, you should know that the 5th equation is not distinct equation, which is useless. With all of those being said, we can draw a conclusion that equation 1, equation 4, and the equation 5 are not necessary equation. In other words, they are not helpful. So to make your circuit analysis easier, concise, and also enough to help us find all the voltages and currents, we only need to keep equation 2 and 3, like this. Okay. This is a very important trick, or say tip, when you conduct the nodal analysis. In other words, how to choose nodes to write KCLs. First, we don't want to choose nodes like a 1 and 4, at where we have 2 identical currents easily identified. Another tip is, we don't want to choose the bottom ground node to write KCL. Keep these 2 tips in your mind. Your resulted analysis is gonna become easier. Now we have 2 KCLs at 2 nodes, and then we can move on to the next step, which is rewrite all of these currents in the KCLs in terms of node voltages by applying Ohm's law. Let's see how we do this. So to first equation, I1 equals to I2 plus I3, how we rewrite it in terms of node voltages. Here are the answers. Let's see how it works. Okay. So we first of all take care of I1. We try to rewrite I1 in terms of node voltage. So by node voltage, obviously, I1 is flowing between node 1 and node 2. So we are utilizing node 1 voltage V1 and node 2 voltage V2. Well, of course, we are assuming at node 1 the voltage is V1, at node 2 the voltage is V2. And we are seeing a resistor here, which we can apply Ohm's law on. So obviously, V1 minus V2 divided by the resistance 9 kilo ohm equals to I1. This is nothing but Ohm's law again. But be very, very careful. You need to follow the I1 direction here to write this voltage equation numerator. In other words, I1 is flowing from node 1 towards node 2. Therefore, in the numerator, it must be V1 minus V2. Current is flowing from the higher potential towards the lower potential. This is a very, very important tip when you rewrite inverse in the second step here. Following the same idea, we take care of I2 here, trying to rewrite I2 in terms of node voltages as well. I2 is here, as flowing between node 2 and node 5, and from node 2 towards node 5, as labeled here. Therefore, the numerator here is V2 minus V5, divided by the resistance value 6 kilo. I3 as the next one. I3 flowing from node 2 towards node 3. So we are writing V2 minus V3 rather than V3 minus V2. And then divide by the resistance, current I3 going through. So this is how we rewrite the first equation, the KCL at node 2. The resulted equation is in terms of node voltages. This is the final nodal analysis equation we should have in the quiz or exam in future. Next, let's rewrite the KCL at node 3. First, we need to take care of I3, following the same idea. Well, actually, we are copying the last term from previous equation. We already rewrite I3 over there, right? So we just copy I3 here. And then we take care of the I4 here. I4 is flowing from node 3 towards node 5. So we are using V3 minus V5 divided by the resistance going through 4 kilo ohm here. So here we go. I5, same thing. Rewrite I5 in terms of voltage, V3 and V4. We can write V3 minus V4 divided by 9 kilo ohm for I5. No problem. However, in that case, we are introducing one more unknown, V4. So instead of that, the better idea is write I5 in terms of V3 and V5. In other words, V3 minus V5, following this path, divided by 9 kilo ohm and 3 kilo ohm equals to I5. Final form of the nodal equation at node 3. So look at these two equations. Obviously, we have V1, V2, V3, V5, 4 unknowns. However, only 2 equations. We can't find anything. So we need additional information, or say additional equations. What are they? It is very easy to notice that, first of all, V5 is nothing but the ground, as we already said. Therefore, V5 is equal to 0. Very useful. And also, if you observe carefully, V1 is equals to the voltage source 12 volt. These could be considered as another equation. So now we basically can consider this scenario as 1, 2, 3, 4, 4 equations and 4 unknowns. We are all set, or say we are ready for algebra calculation. Or you can also consider the scenario as 2 equations, but only 2 unknowns, who are V2 and V3. Anyways, we are ready for algebra calculation. And by some algebra, we are able to come up with the V2 and V3 value, from where we can go further for the current. Since we said both nodal and mesh analysis are eventually for finding every voltage and every current, basically everywhere in the circuit. How to find the current? I1, again, we have clearly discussed here. I1 is equal to nothing but V1 minus V2 divided by 9 kilo ohm. Same thing for I2. We have already discussed here. It is equals to V2 minus V5 divided by 6 kilo ohm, and so on, so forth, for the rest of the currents. So is there anything we are missing here? If you watch carefully, actually, we have V1 here, check. V5 here, check. V2, V3, obtained. All of the current, obtained. Only V4 left. So how to find V4? There's more than one way to find V4. However, the easiest way is still applying the Ohm's law. So V4 here is equals to the current of 3 kilo ohm times 3 kilo ohm. According to the I3K current direction here, downwards, it's going to introduce a voltage with this polarity, which is exactly the V4 voltage polarity, which is from V4 itself towards the ground, positive, negative like this. Therefore, V4 is directly equals to 3K times I3K. So be careful the passive sign convention. Very, very important. And I3K here is equals to nothing but I5, as we have discussed. So V4 is equals to 3K times 1/8 milliampere. So since we got every current and every voltage we want in this circuit, let's think about one thing. Okay, I need to remind you that in the real problem, exam or quiz, we might only ask for one particular voltage or one particular current in the circuit. So when you write equations, you might need to think about which equation you need or which result is sufficient to answer the question. Okay? In other words, you don't have to do everything. You don't have to calculate everything out, because the question is only asking for one of them. So how to identify the results and how to find that particular result is something you need to be careful. We will go through examples to see how that should be paid enough attention. Here is a last thing I want to talk about, nodal analysis. What if you have a current source in the circuit? So keep this question in your mind. In the following examples, pay attention on the solution.